Hello, I would like to present our publication titled Numerical Investigation for the Design of Rectangular Concrete Encased Steel Composite Columns. My name is Ozgun Ergun. I'm a research assistant from University of Luxembourg and I work with Professor Markus Schaefer. With him we co-author. Contents of my presentation are as follows. First is the composite columns under compression and bending in Eurocode 4. What is the methodology used in Eurocode 4 for composite columns under compression and bending? This is interaction curves based on section plasticity. And then we will focus on composite sections with concrete on section exterior, namely rectangular concrete encased steel sections, which will also be referred as CES. And then we will go on with tests from literature with this section typology. And then we will assess the Eurocode 4's methodology via find element method, and we will present alternative approaches by strain limitation to create the interaction curves. And then we will compare these different approaches, and then we will conclude the presentation. So composite columns under compression and bending in Eurocode 4. As almost any code, Eurocode 4 also uses interaction curves to assess the capacity calculation of composite columns. Interaction diagram has the typical shape as shown on the left. On the x-axis it has the moments, and on the y-axis it has the axial force. And Eurocode 4 takes a plastic section approach, which is assuming that the section reached plasticity, both concrete and steel, and having pairs of moment and axial forces at which the section fails. And changing the neutral axis steps along the section, we will find all the points on this solid line, which would be our plastic interaction diagram. But to make it easier, Eurocode allows us to use 4-point interaction diagrams with points being A, B, C, and D, assuming different states on the section, and then finding the moment and axial force pairs, and then connecting these points to have our simplified interaction curve. So point A will refer to pure compression, where the concrete, structural steel, and the reinforcement will be under full compression and they will all be reached plasticity. Point B will be shown here, will be pure bending, and there will be no axial force on the section. The section will fail only due to bending. And then point D will be the point at which the neutral axis is on the centroid, as shown here with the stress distribution. And point C will be neutral axis mirrored from B about the centroid. So only finding these 4 points will allow us to create our interaction diagram according to Eurocode 4. But because this interaction diagrams is based on section plasticity, so assuming all the members on the section, concrete and steel and reinforcement, reach their plasticity at the same time, we have to have a correction factor to overcome this assumption, because we know that the concrete is a very brittle material compared to the steel, and it has a strain limitation much lower than the steel. So to make up for this, there's a factor called alpha m in Eurocode 4, which will be multiplied by the moment values to kind of offset this interaction curve to the left. So from the blue dashed line, we will go to red dashed line. And these alpha m values depend on the yield strength of our structural steel, which is then 0.9 for concrete, for steel strengths between S235 to 355, and 0.8 for S420 and S460. We don't have values for higher strength steel, because the current Eurocode 4 limits the use of this method for concrete up to C50 and for structural steel up to C460. So this method can be used for these following section types. So concrete encased steel section and partially encased steel sections, and then octagonal sections, and then tubes. Here we see a rectangular tube, circular tube with reinforcement and without a profile, and here a circular tube with concrete and steel profile inside. So for all of these sections, we can use this approach when the column is under combined bending and compression. But the thing we have to investigate here is these sections. Of course, they differ in many things in geometry, but one of them differ more than the others. It's the concrete encased steel section, because this kind of section has on the exterior the concrete, and as long as the concrete reached its ultimate capacity, in its ultimate strain, there will be it will mean that the column reached its capacity. So we will focus on this one, and we will assess of this if this AM values are good enough to conservatively calculate the capacity of our CES columns, and if it's applicable in case there will be higher strength steels will be covered in the Eurocode 4 in the upcoming generations. And also we checked in the literature for this kind of topology for rectangular CES columns. If we looked for the tests which were done with the section topology, and we were able to find 27 specimens which were relatively slender. We made sure that slenderness was such that L over D, which being the length of the column to the section depth, to be greater than 10. And sufficing this criteria, we found 27 specimens. And of these 27 specimens, 3 of them were high-strength concrete with normal strength steel, 6 of them were high-strength concrete with high-strength steel, and 18 of them were normal strength concrete versus normal strength steel. So most of the tests were normal strength concrete versus normal strength steel. So there aren't many tests which are done with these sections and which are relatively slender. And here you can see the references we took these test results from. And finite element model, using the test results we obtained from the literature, we tried to come up with an accurate finite element model using the software Abacus with material properties of concrete from FIB model code, which has a parabolic concrete stress strain relationship. For structural steel, we use bilinear strain hardening stress strain relationship. For reinforcement, we use elastic perfectly plastic. And finite element types, for concrete, we used volume elements. For structural steel, we used shell elements. And for the reinforcement, we used beam elements. And the contacts, frictional separable hard contact, were defined between steel and the concrete, so the shell and the volume. Embedded region constraint for reinforcement and the concrete. So we don't see it here, but there's also longitudinal and transverse reinforcement which are embedded in the concrete here. The boundary conditions were defined by a reference point tied with rigid bodies to column ends, restrained as simply supported. So here you see a reference point which is tied to the column end face. And here at this point, then we define the rotation and displacement restraints. And the bow imperfections were defined through linear buckling analysis run before the main analysis to get the eigenforms and define bow imperfection with a magnitude of L over 1000. And running our finite element models for all of these 27 specimens, we came up with numerical model versus test, the ratio between the capacity from the numerical model and to test, being used as the accuracy metric. These values ranged then between 0.87 and 1.17 with an average mean value of 1.05. So it had 5% overestimation in average between the finite element model and the real test results. But we deemed it acceptable to be used for future studies. So on the upcoming comparisons, these finite element model results are not used except of showing the load path. But this model can be used in the future for our research. And 3, strain limitation on concrete for interaction diagram. So like we said, Eurocode 4 assumes plastic section capacity and then reduces the moments by a factor called alpha m. And then we here try something else. This is a strain limit on concrete instead of plastic section plus alpha m. So we say the section reaches capacity when the concrete strain limit is achieved. And then we want to try 2 different stress strain curves for concrete. One is epsilon CU1, which is nonlinear, and then epsilon CU2, which is parabolic rectangular. These both are from Eurocode 2. And the comparison for normal strength concrete and steel. So for all of the specimens we have actually in our publication these curves, but I will present here representative for normal strength concrete and steel, high strength concrete and high strength steel, and normal strength steel and high strength concrete, just for representative. So here we can see this kind of section, which is a rectangular concrete encased steel section with the normal strength concrete and normal strength steel. Here are the geometric properties, and this same geometry applies for 3 different specimens. The only difference between them is having the amount of eccentricity of the load. So we don't see a huge difference between the different curves. So here at the exterior, the 4-point plastic section interaction curve, and alpha m times the plastic section is shown as the black dashed line. And then two others are the strain limited interaction curves. And the points are the test results shown as the capacity of our columns. And the blue one is the abacus result, the load path between moment and axial force for two of the specimens we show here. And here we see that for normal strength concrete and steel, all of the methods show similar results, and yeah, they can be deemed acceptable for this method for this kind of sections, for this kind of material property. And next up is normal strength concrete and high strength steel. Here we're showing only one specimen, and which has 96 megapascal concrete failure strength and 380 megapascal steel. We see that the plastic section has the greater capacity, but of course, when it's multiplied with alpha m, then it shows us a similar, very close curve to the strain limited versions. But interestingly, the test result point falls in between inside the interaction curves for all of the cases, which should be actually outside so that our interaction curves predict the failure. And for high strength concrete and high strength steel, we can see the most dramatic difference between the strain limited interaction curves and the plastic interaction curves. And we also have our load path from abacus. Here we see the two different specimens with this geometry, with high strength concrete and high strength steel. And here you can see strain limited approach is much better than in predicting the capacity. It's giving conservative results as opposed to non-conservative results from the plastic section interaction diagrams. And conclusion, of course, more tests are needed for slender concrete encased steel columns. Finite element model presented here seems to be reliable. It can be used for further studies, but possible updates for the model of course exist, namely residual stresses can be used, and rebar buckling and spalling might be modeled more advancedly. For normal strength concrete and steel, no significant differences between interaction diagrams. For high strength concrete, plastic section assumption might be misleading. If Eurocode 4 is to include higher strength materials, it should adapt strain limitation approach or update alpha m values. This was the end of my presentation. Thank you for listening.